Now the subject of paleoceanography. So we've talked about the Cenozoic history and how tectonics affects ocean currents, which affects climate. And I'm going to dive down a little bit deeper here and talk about the climate and how we can record this. So we don't have any sample. We have samples of ancient rocks, but nobody has a jar of ancient ocean water. So how do we study it? And this whole subject is either called paleoceanography or paleooceanography, whether you put the one O in there or two. But how do we do it? So first of all, we need to look at, again, the effects of ice on deposition of sediments. And so we have transgressions and regressions. A transgression is merely sea level rise. A regression is sea level fall. And when you melt ice, sea level is going to rise. That makes sense. If we melted the polar ice caps, which we're very much afraid of today, that makes sea level rise. Well, that's happened in the past. But if we melted all the ice today, you'd see here that, notice the light blue color floods huge portions of the United States. Basically all of Florida would be gone, as well as, New York, Boston, Washington, D.C., most of the Carolinas, Houston would be gone. It'd be a big deal, pretty bad. Contrast that with regressions. 18,000 years ago, at the peak of that Wisconsin glaciation that we talked about last time, there was a lot more ice on land, and when you build up all that ice, it lowers sea level. The water is held as ice on the land, and so sea level is lowered. So notice that the United States, the whole United States, was much bigger 18,000 years ago. You could have walked, hundreds of miles out of Florida into what's now the Gulf of Mexico. So it would have all been exposed here. If you remember last time, I ended by showing that the Earth, particularly for the last couple of million years, has been one of fluctuating from extremely cold to extremely hot, extremely cold, hot, cold, hot, cold, hot, from a glacial period to an interglacial period. You can imagine that what happens is the land floods, it drains away. It floods, it drains away, it floods, it drains away, and there's no guarantee that it ever really stops for long where we consider it stopped today. We take it for granted that, New York, Houston, Baton Rouge, they are on the coastline today. They always will be. Not necessarily. There were times in the geologic past where they were hundreds of miles from the coast. There were times in the geologic past where they were completely underwater, also hundreds of miles from the coast. So how do we get to this? How do we study this? And again, this goes back to studying the skeletons of these ancient creatures, in particular forams. So the scale bar here, that's 10 microns. So these are things that are smaller than a millimeter in size. It's a single-celled creature. Picture a little amoeba stuffed in a shell that it grew. So look at these beautiful shells. Here's another example of one right here. They grow very, very detailed, beautiful shells. They're wonderful to look at under a microscope. And they can be very, very plentiful. Here's a whole bunch of these things. There's forams as well as other organisms here. These sort of basket-shaped things and the spindle-shaped thing. Their skeletons are made of silica. They're things called silicoflagellates and radiolarians. And then here's a diatom. This is a plant, a single-celled plant that grows a little skeleton around it. And as we mentioned before, if these are present by the uncounted trillions upon trillions, then they produce the rock-type chalk. All right, so all of these things, forams, silicoflagellates, radiolarians, diatoms, they're planktic creatures living in the ocean building skeletons. They can be abundant enough that their bodies either form all of the sediment or a prominent part of the sediment. All right, now a little bit of chemistry. The element oxygen has an atomic number of 8, meaning it has 8 protons. The isotope that is most common is oxygen 16, which has 8 protons and 8 neutrons. Notice that the 8 protons plus the 8 neutrons, 8 plus 8 equals 16. If you find an oxygen atom on planet Earth anywhere, in the oceans, in a skeleton, in the air, whatever, it's going to have mostly oxygen 16. Oxygen 18 also exists out there. And that also has the same 8 protons. That's what defines oxygen. But it has extra neutrons, 10 neutrons. So it is partially heavier. And it is ever so small, the weight difference between oxygen 16 and 18. Just 2 neutrons. But it is enough so that when water is evaporating, the O16 atoms vibrate faster, they become water vapor faster, and as you sit and watch a glass of water, here's some sort of artificially colored blue water sitting here. You can imagine letting this sit on your desk or your table or something, and just leaving it alone and watching it evaporate day after day. The water level would go down, down, down. Most of the O16 goes into the atmosphere. So water, you know, is H2O, hydrogen, hydrogen, oxygen. That's what's in this thing. In the water state here, but as it evaporates, it becomes in the gaseous state. There's water molecules floating around here. This will preferentially become more and more rich in this fatty oxygen, O18. So another picture showing essentially the same thing. Here is an oxygen with a water molecule. There's the Mickey Mouse molecule. We talked about that long ago. 2 hydrogen atoms, 1 oxygen atom, but this is O16. So its molecular weight is 18. Here's one of these fatty molecules with O18. Notice its molecular weight is heavier. There's a hell of a lot more oxygen 16, 99.8%, and so this is the one that evaporates more easily, it precipitates less easily, it makes state changes much more easier. Here, not as much. All right, during ice ages, what happens on the atmosphere? So the oceans evaporate, the atmosphere gets enriched in O16. So this anytime there's this transfer of state, change of state from water to gas, it's going to preferentially have more O16. That's the blue bar here. This will rain down. The rain is also water, and so it has this same distribution, more O16, less O18. If we are entering ice house or ice age conditions, then it stays here. It stays locked up as glacial ice. That glacial ice then will also have the same general relationship in that the ice is going to have more O16 and less O18. So notice the O16 bar is higher in the atmosphere and in the glacial ice than the oceans, where O18 is enriched. So there's this weird balance thing going on. And again, this can all easily be modeled by this simple glass jar. In the oceans, as it says there, the O16 is taken up, so the oceans get enriched in O18. And then just a couple pictures showing this, but here's the situation when the world is cold during an ice age. Now, during an ice age, and during any time, you've got organisms living in this water. And these organisms build their skeletons out of something. Let's say it is calcium carbonate. Calcium carbonate is CaCO3. They build their skeletons that have 3 oxygen atoms in them. If they are living in a soup of ocean water that is enriched in oxygen 18, their skeletons will be enriched in oxygen 18. If, on the other hand, they're living in a glacial time period where the glaciers have melted and there's more oxygen 16 in the oceans, it's going to be reflected as well in their skeletons. So again, icehouse conditions. The glaciers grow, seawater is enriched in O18, and sea level drops. During a greenhouse or interglacial conditions, the ice melts, the seawater goes back to what's called normal levels, and sea level rises. So, remember, these skeletons are made of this chemical formula, CaCO3. Instead of sampling the oxygen in ancient water, which doesn't preserve, we sample the oxygen in these ancient skeletons, which are preserved. This is a whole separate subdiscipline of paleontology called micropaleontology, and it's very, very important for these climatic studies. So, in this diagram right here, this gray triangle is supposed to be a generic organism growing its skeleton out of calcite, CaCO3, in a soup of water, which is all this H2O. And if you look closely at all this, all these H2Os, some of them are O18, but most of them are O16. As this animal lives and eats things and incorporates this, elements from this soup of the ocean into its skeleton, it's going to build a skeleton of CaCO3. And here, notice here they have the C, the carbon atoms with oxygen ringing around them. It's going to occasionally incorporate some of this O18. Increase the O18 in the water, you're going to increase the O18 in the skeleton. Decrease it, the animals are going to respond here as well. So, we talked about this way back when we talked about sedimentology in the oceans. We have data, we have miles and miles of core that we have spent literally hundreds of millions of dollars obtaining, drilling these cores in the ocean, and now we are looking at all of these fossils in here, and we take them out and we can literally easily measure the O18 in their skeletons. And we take that to be a proxy for the O18s in the oceans at the time. Now we also have, go back to this, what about the ice? Well, we're not in an ice age period now. There certainly isn't glacial ice covering Wisconsin, but we have glacial ice, the remnant of this, that glacier that was on Wisconsin, and the Wisconsin has retreated till now it's just sitting on top of Greenland. And if we go to Greenland, we can get cores of the ice. The ice itself isn't just pure H2O, it has air bubbles, which is literally trapping the atmosphere as it formed over here. So we've got ice cores and we've got sediment cores. Look at this model again. Sediment cores would be taken in here, and ice cores would be taken in here. If the skeletons of fossil organisms in the cores here are enriched in O18, that would be evidence that the Earth is in a glacial period. At the same time, if we can somehow take a core through ice and ensure that we're looking at the same exact date, let's say it's 13,500 years ago, the ice then would be enriched in O16 and vice versa. So as one amount increases here, it's going to decrease in the other. And in fact, we do this. So again, the ships, there's one of these ocean drilling ships going around the world drilling these cores. We know that these sites are drilled everywhere, studied by scientists, examining them for every possible thing, geochemically, geophysically, but here again, picking little forams out, centimeter by centimeter by centimeter, which again gives you time, and then measuring the oxygen 18 in the skeletons gives you this record then, not just of the rocks, not just of the chemistry of the rocks, not just the changing fossils in here, but the record of O18 through time, which ends up plotting up like this. So, in the sediment, so here's again, giant ice sheet, ocean, and the ocean is getting depleted in O16, enriched in O18. These animals living in the ocean build their skeletons accordingly. And if you look at levels of high to low, you drill a core here, you'll see that the O18 levels do one of these numbers. They go back and forth, back and forth. High values, low. There's a cyclicity to it. If you drill an ice core, and we can correlate the exact same times, then you can look at its pattern and notice it is a reverse, where one has a peak, one has a low spot. One has a peak, one has a low spot. And so we've gone all around the globe and taken these sediment cores that we've spent hundreds and hundreds of millions of dollars on, and now we're comparing it to these ice cores, which we've spent also hundreds of millions of dollars on, both in the north, in Greenland, and in the south, in Antarctica, and this pattern holds. So we know that this system works. And when we look at this, then, we see that the Earth has gone through a series of cycles. So again, notice here, this is sort of the oxygen isotope ratio, the ratio of O18 to O16, basically looking at how much O18 you have. And if you go depth in core, so this is centimeters, 400 centimeters, 800 centimeters, 1200, 1600, and again, that's literally measured as you go through the core here. That equates to time, and we see that the Earth has gone from one of these ice periods, cold periods, to warm. Cold, warm, cold, warm, cold, warm, cold, warm, back and forth, back and forth. And sea level has thus done it as well. This diagram here, to conclude the thing, shows that we live in this line here on the extreme left side.
On it.
On the extreme left side, and as we go back in time, we can see that sea level has risen or dropped over 100 meters. That's over 350, 380 feet, back and forth multiple times. It is spurious to think that climate will always stay the same. It's always changing. And we are currently in one of these interglacial periods. We have been in the past, most recent past, in these glacial periods, but we go back and forth to these things. So that's the first thing, accept that change exists. Now, the concern for global warming is that we are increasing this change far more rapidly than has happened naturally. And will we get into a much, much, much warmer period than these previous interglacial periods? We don't know. But anyway, oceanography, and in particular paleoceanography, is what's going to tell the tale. And this is why millions, and again, hundreds of millions of dollars have been spent in the oceans, and it's not always what you think. It's not studying whales and porpoises and sharks for Shark Week and everything. It's studying little forams so that we can get sediment cores to talk to us about changing climate. And what's happened in the past is our best indicator of what's going to happen in the future.